Hello guys, in this video I'm going to talk about scale invariant feature transform. So I guess this is going to be a little big video because there are a lot of things that I need to cover. So and I'm also going to go a little slow so that you can understand each and every concept in detail. So let's get started. So in my in the Harris properties of Harris video, we saw that Harris is not scale invariant. So if suppose I wanted to match this particular image with this image, I will not be able to do that because this is a small sunflower and this is a big sunflower. So even if both of these sunflowers are almost similar, but then because this is big, so it will not be able to nicely match both of them. So that is what we saw in Harris. So let's see how we can overcome this problem. So one can say that if suppose I scale this image smaller to the size of this particular image, then we will be able to match both of them. So what I mean is, um, over here I have some features that I'll detect in this particular image, and these features will now be matched not only to the original image, the original second image, but to the scaled versions also of the second image. So this is the original image. I've scaled down by some factor, again scaled down by some factor, and these features, a feature over here will be detected to a feature over here, to a feature over here, and a feature over here. So like this, we'll be able to match both of these. So you can see that over here you can see this sunflower is somewhat similar to the size of this sunflower. So this is the step by which SIFT becomes scale invariant. So this is what is the scale space. So I'll talk more about the scale space in my upcoming slides. So now I was talking about the features. So I talked about that there'll be some features over here which will get matched to features over here. So what will be these features? So those features are nothing but blobs. So what are blobs? So blobs are these circle kind of a thing. So this black dot or black circles that you can see over here, over here, over here are examples of blob. Even this white patch over here can also be said as a blob. So these blobs have very nice information about the particular surrounding or the particular local image patch. So these blobs are something that will be my features, or the center point of the blob, or the points in this blob are good features. So SIFT uses blob detection to select the features that we are going to match. So you can see in this example also that suppose that there are a lot of sunflowers. So in these images you can see that over here the smaller sunflowers are seen, the smaller blobs are seen. So these blobs are seen. But as and when you go ahead, you can see that you can only see these bigger blobs now. So we'll see this in detail. Also, this image was generated from this very nice site. So I'll give this link in the description below. You can also use this site. So now let us step a little back for understanding how can we detect these blobs. So the task over here now is to detect these blobs, and these are going to be my features. So for that, let us go a little step back and understand edge detection first. So this is an image, suppose that I have, and I take only a row of this image and plot it over here. So these are 0 pixels because it is black, and this is white pixel because this is 255 because it is white. So 000 and suddenly 255. So now what I do is I take a derivative of the Gaussian. So this is the derivative of the Gaussian, and I basically convolve both these two. So in convolution what happens is you take one signal, you flip it, and then basically multiply it with the other signal, and and keep on shifting it. So I have kept this over here. So this is like this thing multiplied with this is almost 0. This thing multiplied by this is again almost 0. So the output is almost 0 over here. Now, as and when you move or shift this particular signal, you will see that over here you will get all 0 values. But when this edge has occurred, what happens is this greater amplitude gets multiplied to even greater amplitude, and this is still 0, and that addition will give you a big quantity. So that is this big quantity over here, this peak over here. So we know this is a simple edge detection that I have done using a derivative of the Gaussian. Now let us see what happens if we take the double derivative of the Gaussian. So this was the derivative of the Gaussian. I again do the derivative of this particular thing. So wherever there is a change, so you can see a maximum change over here. So there the output is high. There the output is high, and here you can see that the slope is almost 0. So sorry, here you can see that the slope is almost maximum. So the output is almost maximum or in the negative direction, and here the slope is 0, so the output is less. So this is the second derivative of the Gaussian. And now let us see what happens when we convolve this with this. So it can also be seen like this. This was the previous output, that is convolution of this signal with this derivative of Gaussian. You just take this derivative. So instead of taking this derivative over here, you take this function's derivative, and you will get this function over here. So this is nothing but the Laplacian operator that we say in edge detection. So what it says basically is that when I'm taking a derivative of this thing, so here you can see the slope is very high. So a high input, a high output, and here the slope is less. So almost 0 slope. So this is 0, and then high. So this is what we have. So please notice the difference between this and this. Over here, wherever there is an edge, it has maximum output. So here, wherever there is edge, the derivative is maximum. But over here, wherever there is an edge, there is a 0 crossing. So there was an edge over here. So over here, the function is going crossing 0 point. This is the 0 point. So this is one insight that you get from a log. So coming to the point, now you can take this as a blob over here. So suppose this is a white color patch and there is black around. So this is like something like a blob. So when I take a row of this blob to understand in 1D, so this will look something like this: black, 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 suddenly white, black, black, white, black. So now let us see what happens when we convolve this with the Laplacian operator. So this will be your output. So you will see that since there is an edge over here, there will be a 0 crossing over here, an edge over here, a 0 crossing over here. So that's fine. But you can see that as and when the I'm scaling this particular thing. So this was this big. Now I'm scaled down to this. Then I'm scaling down to this. Then I'm scaling down to this. So you can see when I have scaled to this particular point, you can see now there are no two different edges or two different 0 crossing, but there is only one maximum kind of a thing. So you can see that whenever the size of the Laplacian that you are using, this particular size, when that is equal to the blob size, you get a maxima. So please understand this. Here you could see that the size of the blob or the Laplacian. So this is the output, but when the size over here as so when you put the Laplacian operator on this particular thing, if the size matches to the blob, then you get a maximum output, a maxima like this. But when they are not matched, you get something else. So this is an important, very important thing for blob detection. So now the magnitude of the Laplacian response will achieve a maximum at the center of the blob, provided that the scale of the Laplacian is matched to the scale of the blob. So now we just want to see where there is maxima or minima in the Laplacian output. So this is the image. I will pass it through the Laplacian filter, and we'll see where it is maxima. But since we need to match the scale of Laplacian, that is the sigma value of Laplacian, to the blob value, so we'll basically convolve this with lot of Laplacian. So this will be clear in a moment. So it'll be clear from these slides. So these slides are taken from Kristen Grauman slides. So very nice PPT. You can click on this link and go to the her PPT. So here this is the original image. Suppose that I take a Laplacian filter of this size with sigma like this. So you can see over here that you can now detect these small sunflowers. You can see these maximas. So the light blue is a bigger value, and this dark blue is low value. So you can see these particular output. Now suppose I increase the size of the Laplacian. So now this sigma is 6. Sigma is the variance of this Gaussian that I've used. So this is a Laplacian of Gaussian, that is the double derivative of the Gaussian. So you can see that when I increase sigma, now I am able to detect the little bigger range of the flowers, and you can see now the smaller range of flowers are almost non-detectable. Now further I am increasing the range of sigma, so you can see the further the ahead flowers are detected, the bigger flowers are detected. So this is a very important intuition over here, that if you want to basically match this particular flower with say this flower, so what you will have to do is you will have to bring the scale of this flower to as small as this flower. So that is the intuition for the scale space. Now, this Laplacian is a very time consuming thing. It is a complex operation. You have to take the double derivative and scan it through the image. So instead of using the Laplacian of Gaussian, we approximate it using the dog, which is difference of Gaussian. So the Laplacian of Gaussian is given like this, where you have this Gaussian function and with variance sigma, and you take its double derivative in x direction, double derivative in y direction, add both of them, multiply with the variance that you have squared, and that is your Laplacian. So this is a complex operation. This takes a lot of time. So you can approximate it using a difference of Gaussian. What you do in difference of Gaussian is you take a Gaussian which has a particular variance like this, k into sigma. So this is something like this. So this is an image which has k into sigma variance, a Gaussian filtered output. And now there is another image that I have filtered through this only sigma Gaussian image. So this was so there was an original image. I filtered that image with a Gaussian that is having variance as sigma, and take the minus, and this is the output. So you can see that this red is your dog output, that is difference of Gaussian, and yellow is your Laplacian. So you can see they are quite similar. So it is not overlapping, they are not the same, but you can approximate it and reduce a lot of computations. So this is again taken from this particular slide. So now from Laplacian we are going to use difference of Gaussian. So now that brings us to the entire scale space. So in the first slide we saw that different scales are important. So for that we have used different, we are going to use different scales of the image. So this is the image, and we this is the image, this is the same image scaled by half, this is again it'll again scale by half, and the story. So that is one thing that is important in the scale space. And the other thing is, since we want to detect blobs, so for that what we need is difference of Gaussian. We just saw dog. So what we do is, we have this particular image, say I have this image, I will blur it with a Gaussian filter having variance as sigma. So this is my Lx comma y comma sigma, this thing over here. Next, what I'm going to do is, I'm going to blur this filter, this filtered image again with a Gaussian that is having Lx y comma sigma. So what is going to happen is, this is blurred with this is the original image blurred with sigma, and then this is blurred with sigma. So with respect to the original, this has uh, sorry, this is blurred with sigma, and this is blurred with k sigma, which is written over here. So this is sigma, this is k sigma. So there is then we'll take the difference of both these outputs, and that will be the difference of Gaussian. Further, there will be k square sigma. So this was blurred with sigma, k squared sigma, k cube sigma, and the story. So like this, we will have this particular range of blurred output, which is shown over here. And then after a particular range, so say 6 over here, so after 6 times blurring, I'm going to scale down the image and again do the blurring, again scale down, again do the blurring, and the story. Next, what I'm going to do is, I'm going to take the difference, because that is what we want. We want difference of Gaussian. So these two images took the difference, I have it over here. These two images took the difference, I have it over here. So like this, I have this difference of Gaussian output. Now we saw that we need to now take the maximum. So this maximum will tell you the location of a blob. So since we are scaling the image, and we are also using different values of k variance k sigma, so what is happening is, in one particular octave, so this is an octave, this one particular thing. So in one particular octave, we have different scales of this what we say Gaussian, difference of Gaussian, and in the next octave we are scaling the image. So we are finding that particular scale for which both of these become equal, and we get a maxima. So these are the interest points. So we have to detect these maximas. So the next step is basically to detect the scale space extrema. Now this can be a maxima, or this could also be a minima. So since this is like 0 0 0 and 1 and then 0, so this is like this is one particular extrema. If it would have been 1 1 1 and 0 and then 1 1 1, then it could be the opposite of this thing. So it is this extrema that is important. It could be local maxima, it could also be local minima. So in order to detect this, what we do is, in a particular difference of Gaussian image, so we start with the second image over here. What we'll do is, we will say this is that second image over here. So now suppose that I am calculating for this pixel. So what I'll do is, I will compare this particular pixel with its 8 neighbors and its 9 neighbors that are in the top scale. So that is the 9 neighbors that are over here and the 9 neighbors that are over here. So like this, I will get 26 points, and I will see whether this particular pixel is the minimum of all these 26 points, or is this particular pixel the maxima of all these 22 or 26 points. So that is those points I have to detect which are maximum in their surrounding neighbors or the minimum in their surrounding neighbors. That is my task. So this is what we call as the scale space extrema detection. So when we do that, we see this kind of output. So suppose this is my input image, and I do the following steps. I blur it these many times, take the difference of Gaussian and the story, and then do this scale space extrema, I get so many feature points. So many points have local minima or maxima. So you can see this is quite of there are a lot of noise over here. Now these are not good features to match. These are not good features. So we'll have to remove some of the points which are not needed. So for that we need something that is known as feature point localization. What is feature point localization? So we have seen that here everything is discrete. That is, suppose this is my x direction, so this is the image, this is x direction, y direction, and this is the scale direction. So my x is discrete because I have pixels, y is discrete pixels, and my scale is also discrete. You remember there is this sigma, then k sigma, then k square sigma, and the story. So this scale space is also discrete. So now there are two things over here. First, there could be a particular maxima in a scale which is in between both of these. Since this is not continuous, so I cannot find that point, but at least I can interpolate. So that is what we are going to do first over here. So we are going to interpolate the particular function using a Taylor expansion to fit a 3D quadratic surface. So now I am in 3D, I have x, y and scale, and I want to find out what is the maxima, or which particular pixel has maxima or minima, the extreme values. That is what I have to find out. So let us get first clear with the notations. So I have z0. What is z0? So z0 is the location of the actual pixel that is detected. So till here we have detected all these features which have either minima or maxima in their neighborhood. So those, so considering one particular feature out at that, so suppose I consider this feature over here. So this is this point over here, and its xy sigma is z0. Similarly, what is z? So now what I feel is, if suppose it would have been in a scale which is greater than this scale but less than this scale, then I guess there could have been a minima or a maxima. So this will be that important point. Other than this, I could not find this point because I never searched in that point. So this is a kind of an interpolation that I'm going to do. How do we do that? So this is the Taylor series. So I have, what is d? So d is the pixel value at that point. So the pixel value over here is denoted by d of z0, because this point is z0, this is our z0. So d of z0 is the pixel value at this point. What is z? So z is this delta x. So that is, if suppose there is some difference in the x direction from this pixel and this pixel, then delta y and delta sigma. So the upper difference is in difference in this scale, difference in this scale, difference in this direction. So that is my z. So I want to find out the pixel location at this point, where this is in between both the scales. So actually it is not possible because I never computed an image like that, but using Taylor series I can do that. How? So I have this formula. So d of z0 plus z, so that is d of this pixel, so that is the pixel value at this particular position, can be given like this. So this is the Taylor series. Now I want to find out whether what is so there is this function over here which I have approximated using the Taylor series. I want to find out a maxima or minima wherever there is this maxima or minima. So this z is what I want to find out. How much do I move in a particular direction so I get maxima or minima, some extrema. So for that we call our derivatives. So we just find the maxima or minima by differentiating this particular function with respect to z, because that is our variable over here. We want to find out this. So equate the differentiating this with z and equating it to 0. Let's see what we get. So this is a little bit maths. So this was our Taylor series equation. We just differentiated this with respect to z. So this term becomes 0. This term becomes, so there was this z term over here that will go, and this transpose will go. Next, this is half times. So this is like a quadratic kind of a thing. There is z transpose this thing into this. So this just becomes this particular. So this is a matrix. So this matrix into z. So now I'm replacing the notation with z cap, because this is that particular z. This is that particular z where we have maxima or minima, and that I'm equating it to 0. So now doing a little bit algebra, I am taking this particular thing over there, cutting the 2, I get this thing. Now this is a matrix, so I just take an inverse of this particular thing and I get my z cap. So z cap is given by this equation. So now you can see that I have this Taylor series approximation. Now if I put the value of z cap over here in this z, then I will get the value of d of z naught plus z. What is d of z naught plus z? D of z naught plus z is the pixel value at this location. So I've used Taylor series to interpolate this thing, the pixel value at this location. So I am just putting this z in this over here, over here, over here. So yes, so here there's this trick that this particular z I am just keeping as z cap. This particular z also I am keeping as z cap. So there is d, this is same, this is same. Here I have replaced this by z cap. Over here what I've done is this z transform, z transform, this transpose, this is transpose, z transpose, this I'm replacing with this particular quantity. Why, you will get to know that. So only this thing I'm replacing with this quantity, other I'm just keeping as z cap. So what happens is, this is transpose, so this goes and there's this transpose over here, then this transpose comes inside, so this will come ahead, this will go behind because of transpose. So this will happen, and now you can see that there is this squared matrix over here, a square matrix over here. This is what we call as a Hessian matrix. So it is seen that this particular matrix is symmetric. So when I take the inverse and transpose, so that will also be symmetric, and this both will basically cancel each other. So that is a property of this Hessian matrix. So this both becomes identity, and I have so this becomes identity, and this z cap will come ahead. So that is what I have over here. Now you can see that this is del z by del d by del z at z naught transpose. Here also there is del z by del z, z naught transpose. There is a z cap, z cap. So only the coefficients are different. There is 1 over here, there is minus half over here. So you can take this particular thing common and you'll have 1 minus half. So that is plus half. So this is the value at that particular pixel. The value at that particular location, the interpolated value, and this is maxima or minima because we have derived that particular thing. So now we have interpolated this particular thing to some other scale and some other xy where it is minima or maxima. So this image is taken from this original paper by David Lowe. So it is a very nice paper. It has lots of citations. So this paper has one of the highest citations in literature, in computer vision literature. So giving a summary, so a lot of maths. So in summary, what happens is you get an extrema, a particular feature using those difference of Gaussian. Now what you do is you just calculate the z cap using this particular equation So this del z by del z, how will you calculate this? This is nothing but a vector like this, del d by del x. So that is difference in x direction. So this is my x direction. So what I'll do is, this is the feature that I've got. I take this particular neighbor minus with this, that is difference in x direction. Similarly, difference in y direction, this feature minus this, so that will come over here. Similarly, difference in the d direction, d what, difference in the scale direction, so that will be this feature minus this. So like this I can calculate this particular vector over here. Now if suppose this vector is a, so a into a transpose will give you this matrix. So that is precisely what I do. Next, you put this z cap over here, and this you have over here, and calculate this thing. You have d of z naught, that is the pixel value at this location, and add. So by that you will get d of z naught plus z cap. This d of z naught plus z cap is the pixel location at this particular point. Now if this particular pixel location that you found at this point, if it is less than 0.03, that is so here all the pixels are in between 0 and 1. Now these pixels are not in between 0 and 255, but they are in between 0 and 1. That is the range of the pixel. So either a pixel can be 0 or 1, or in between them, 0.5 or something like that. So if it is less than 0.03, this pixel over here, then I discard it. Even if this is less than 0.03, I am going to discard it, because it is something that is known as low contrast image. So if I give you a idea of what is low contrast, so you can see that there are some local maximas over here also, but this is not important. You can see these maximas are more important than these. So these are maximas, but they are not that important, so we neglect these particular maximas. So that is what is low contrast points. So those are the low contrast points. So those we neglect it when if it is less than this particular value. Also, if suppose we get del z, so if we get del x and del y greater than 0.5, so that means that this I have a point over here, and my del x or del phi is greater than 0.5, so it is more towards this particular pixel. If it is greater than, if del x is greater than 0.5, so you can see that it is more towards this pixel. So we change the value of z naught then. So then I will not take this pixel, but I will take this, its neighboring pixel over here. So that is what is written over here. So after you do that, you take this as z naught, and again start this particular process. Again calculate z cap and d of this thing. So that is an iterative kind of a process. But if suppose they are moving a lot, you calculate z cap for this pixel, and it turns out to be greater than 0.5. You go to this pixel, again greater than 0.5, and like this it is oscillating. So then you discard that pixel and say that it is unstable. So that is what. So this was quite a mathematical kind of a part for this particular for this SIFT, but further things are quite easy. So after feature point localization, you can see that you will get this kind of a image. So here you can see a lot of noise is gone from here. You can see these noise points are gone. So now you can see still there are a lot of features. You can see a lot of features are on this edge. Lot of features on this edge. So because Laplacian also detects a lot of edges, so because of that you get a lot of edge points on these edges. So next thing that we have to do is we have to remove these edge points. We just want the corner points. So we do that by using the Harris method. So in Harris we used to get this H matrix. Suppose you have not seen Harris, so you can click this video over here. That'll take you to the Harris video, and there I've shown how we can get this H matrix. So the eigenvalues and eigenvalues only the eigenvalues of this particular H matrix have information about whether a particular point is on edge or on the corner. So here SIFT paper has used this kind of a thing. So there we used a different form, but here we are going to use this form because the paper uses this. So by using, I guess, trial and error or some thing, they found out that this particular thing is better in SIFT or this particular algorithm. So they took the trace of this matrix squared upon the determinant. So if alpha and beta are the eigenvalues of this matrix, so it will be something like this. So we know that if it is an edge, either alpha or beta will be low. So its addition will be relatively equal to the other. So if alpha is minimum, so the addition will be equal to beta, and beta is a big value. So one is less and one is big, if you remember the Harris case. So this will be like beta squared kind of a thing, and this will be a small quantity because alpha into beta, where alpha is small and beta is big, so this will be a small quantity. So for an edge this output will be big, but if it is a corner, both of these values will be big because it is a corner, so both of alphas and betas will be big. And for that, what will happen is alpha plus beta the whole square will also be big, alpha beta multiplication will also be big, so this will turn out to be a small quantity. So for corners this will be a small quantity, and for edges this will be a big quantity. So what the paper suggests is we can take a R, which is nothing but alpha upon beta, beta upon alpha, I guess. So, or just replace alpha by R beta and do some calculation, and you can set a threshold on R, how much you want the ratio of the eigenvalues to be. And this paper takes 10. So if you put R is equal to 10 and put that into this formula, all those pixels that don't that follow this criteria are kept, and which don't follow this criteria are removed. So any pixel that is on the edge will not follow this criteria, and that will be discarded. So after removal of edges, you can get a pixel, you can get a value like this. So let us stop over here. So till now we have seen how does the SIFT detector detects the following points over here. So we have seen how the features are detected with the SIFT algorithm. In the next video, we are going to see what is a SIFT descriptor. So there is this new thing that SIFT algorithm gives you, that is a descriptor for each particular feature. So that is what we are going to see in the next video. Also, I am going to put the links of the sources from where I have taken the particular slides and information. So please also go through them. That will give you a better insight. And I know that it has become a long video, but it was important, so I request you to just go through the video nicely, and that's all. If any doubts, you can always post them in the comments below. Thank you so much for watching. Thank you.